let this circle represent the motion of the first push pin, and let this circle represent radius 10 centimeters. Then the position of the push pin, if the circle is rotating at a constant angular velocity, then a snapshot of the r of t vector at equal time intervals, a series of snapshots, would give us an r of t vector that's rotating around the circle something like this. Now let's say that we want to rotate around the circle once every 6 seconds. Then we can let our r1 vector, r1 of t, equal 10 centimeters times the cosine of pi over 3t times I plus 10 centimeters times the sine of pi over 3t times j. You can verify that if t changes by 6, that pi over 3t changes by 2 pi, which gives us a complete cycle around the circle. Let's say we have another object. Let this domino represent the beam, and let this represent the end of the beam. Now if this beam is rotating as it travels, then you can see that the path of this endpoint will eventually come back to the circle. We'll start out here and it'll come back into the circle, and then as we continue to rotate, it'll stay inside of the circle until it comes back to the circle and then again moves outside of the circle. Now, depending on how rapidly this moves, if it moves it rotates very rapidly, it might complete a loop inside the circle and back in a short distance, or possibly in a much longer distance. Let's let the r2 vector be, let's say this is 3 centimeters times the cosine of, let's say this thing is rotating twice as fast as it's moving around the circle, completing a rotation in 3 seconds rather than 6, so that this thing will complete a rotation and be back to its original orientation by the time it reaches the opposite side of the circle. Then r2 of t could be 3 centimeters times the cosine of 2 pi over 3t times I plus 3 centimeters times the sine of 2 pi over 3t times j. At the initial instant, our r1 vector would be here, the r2 vector would be here, so that the position of the object would be here, and that position could be described by the r1 plus r2 vector, where this is understood to be r1 of t and r2 of t. Now, if this thing rotates at twice the rate of the circle, then when we get here, this thing will be at an angle that's twice as great as this angle, and that would be what our function would tell us, and we would have our r1 plus r2 vector here. If we continue to rotate, and I'm not going to draw a vector for every one of these, if this thing continues to rotate at twice the rate of this, then this angle will always be double this angle, so that by the time we get here, our point might be out here, our r2 vector might be here, So let's see, here's our R2 vector, here's our R1 vector for this instant. Now our R1 vector is here, R2 is here, and our position vector R would be out here. As we continue to rotate, doubling this angle, by the time we get here, the R2 vector might be back in the neighborhood of the circle. Our position vector would be here, and so forth. So our path might look something like this. The path would then continue to the inside of the circle, and the motion would continue accordingly. This is a kind of a model of an amusement park ride, a common amusement park ride, where you have a car that rotates on a beam in a circular motion, and the car itself rotates within the beam. Matter of fact, that was the motivation for this model, because there was a local carnival recently, and took my grandson. He really enjoyed that ride, but he's only 10 years old and he's not able to do the mathematics of it. We'll continue in a minute.